Basically, this boils down to, let me continue the story about trying to figure out some, study method that would work for me. Because, as I said before, I was spending all my time studying, but it wasn't paying off. And basically, what I finally found that works is I kind of was studying the wrong way. I wasn't paying attention to what the professor was talking about. The most important stuff that you want to learn is what the professor thinks is important. Right? And does the professor cover the book, end to end? For example, in the thermodynamics class, the book was 900 pages long. And when I study, I try to learn everything. And so I'd start off in chapter 1 and learn it, from beginning to end, and learn everything in there, or try to learn everything. And quickly I find out, I just ran out of time. Fell way behind. And so that shifted the way I thought about studying. Rather than trying to read the chapter 3 times, like once before lecture, once after lecture, and maybe once before the exam, I didn't. It was impossible to read it that many times. So instead, I didn't even read the chapter before coming to class. In fact, I didn't even skim it. I just came into class expecting not to know what's going on, but that was okay. Of course, if you read the chapter before, you're going to be much more aware of what the professor's talking about, and it makes it easier to follow. But eventually, you get to a level of class where, everything is hard. Some people, they come into a class like this, and they think that, if the professor can't explain it, and it doesn't click right away, and you don't understand all of it, and you can't do every single problem, then there's something wrong with the professor. But, quickly you got to get over that kind of thinking, because when you go to these scientific seminars, you sit there and sometimes you're utterly confused with what's going on. You register bits and pieces of information, but you just don't, it just doesn't quite click, right? But that's okay, because I kind of expected it to not click completely. Some things are easy. Some things, you'll pick up right away. Oh, that's easy, right? And you can go home and do it right away. But, this is, chemistry is not necessarily easy. It's like if somebody were playing the piano, like Chopin or something, and you watch them and you go, oh, that looks easy. Are you going to be able to do it right away when you go home? No, and of course you aren't going to have that attitude towards chemistry either, because a lot of this is not going to be that easy. You don't just watch and learn. You also have to do some practice and some work. Well, I was ready to do all the work, and then some, but I was doing all the work in the wrong places. My work wasn't focused on what was important. And what's important is what, was discussed in class. That was most important. And so eventually I figured all this out, and I changed the way I study. And the way I studied was I try to write down as much as possible in lecture. Bits and pieces here, maybe I don't have the whole picture. And I can't write that fast. A lot of study books say, learn shorthand. If you learn shorthand, then you can write down everything the professor says, and you aren't going to miss anything. And that way, you can get much better grades. Well, I was slow. And so to make up for that, what I would do is right after class, it's best to do it right after class, because there are other books I read about memory and how much memory you lose. Like, for example, do you remember what you ate 1 month ago on Tuesday? For breakfast? Maybe you eat the same thing, but maybe you don't. Or, do you remember what you were doing? Well, maybe. But, those types of memories start to fade, right? Unless, some people have photographic memory, but I certainly didn't. And so I would start losing the memory rapidly. And if you look at a curve about memory loss, if you wait to review your notes like a month later, a month later, it's gone. And so the best time is right after class. Right after class, you might not have been fast enough to write it down, but you still remember certain things. And so what I do is I read the notes and then fill in any blanks from memory that I could. Okay, and still there are going to be parts that are confusing, parts that don't make sense. And so what I would do in that case is I would read the chapter. So after reading my notes and filling in as many blanks as I can, I knew, there are certain things I just didn't understand that didn't make any sense. And so when I went to read the chapter, I would focus on those sections. And so I just skim. Well, this wasn't covered by the professor, so just skim. Or this is easy. If it's easy, just skim, skim. And then you can read quite rapidly if you're just skimming the chapter. But when it gets to something that's confusing or difficult, then you slow down and read it. And so the sections, I wouldn't read the whole chapter 3 times. I'd read the section that I had difficulty with like 3 times, 4 times, 5 times. And if it still didn't click, you know what I'd do? I would either go level down or I'd go level up. I'd look for a more basic book and read it, or I'd look for a more advanced book and read it. Now, oftentimes the more advanced book was more helpful because they take one paragraph that was discussed in general chemistry and convert it into 5 pages of detailed discussion in a more advanced book, and then it makes sense when you have all that additional detail. And so I was reading a lot, but it was just the stuff that was important. It was the stuff that was covered in class. The stuff that wasn't so important, I just skimmed it. The same goes with homework. If the homework is repetitive, oh, that's easy, it's tedious, right? Then just skip those problems and then focus on the problems that give you trouble, right? The ones that you need help with, the concepts, topics, whatever. Although you can't necessarily do that. At UCLA you could, because they didn't collect homework. And so the homework was just for yourself, and you would do it, just for your own personal benefit. But here, the homework I'm going to collect, because there's this whole push, and I see it all the time. A lot of elementary schools and junior high schools and high schools, they're anti-homework. A lot of those people, what's the use of homework if you can just look it up, that kind of stuff. So you got to get into the habit of doing homework. So I'm going to be collecting the homework of those particular problems. All right, and so that way, we covered a huge book, but we didn't really cover the huge book. We only covered certain sections of the huge book, and if you focus on the sections that are important, and what are the sections that are important? The sections that are important are what the teacher says are important, not what you might think is important. What I thought was important was everything. I didn't want to miss anything because I thought if I had holes there, I'd suffer on the other concepts, but that wasn't the case. Okay. All right, so that's the end of that story. Whatever, maybe you don't need any tips. Maybe there are other tips other people want to share, but those are the tips that I wanted to share with you. All right, so let's take a look at this problem we left off with. Last time. All right, this is for a solution containing 6.38% para-dichlorobenzene by mass. Did we finish this, the sig figs on this? The sig figs are tricky because this is 5 sig figs, this is 4 sig figs, this is how many sig figs? 2 sig figs. So your final answer should have how many sig figs? 2, true or false? Your final answer should have 2 sig figs, true or false? True means always true. What do you think? Your final answer should have 2 sig figs. Yes or no? No. We don't know how many sig figs are going to be in the final answer because why? Not because of the uncertainty. The uncertainty is kind of measured by how many sig figs you have. We don't know how many sig figs we're going to have because we were dealing with two different sets of rules. The rules for multiplication and division are different than the rules for subtraction and addition. So when we have a mix-up of rules like that, we just have to be consistent in one set and then move on to the next set. And so did we finish this problem or not? No? Okay, let's go ahead and finish this problem, and then we'll talk more about this. One thing I don't like, what don't I like about this equation? No units. You know, this is like the engineering equation. And in chapter 1, they talk about this disaster about the units. You know, you're given an equation like this. Well, without any units, yeah, it's very easy to make a mistake. But anyway, let's go ahead and figure it out. So we want this density. And so what did we do so far? Let's see, we got this on one side, 1.836 times 10 to the minus 3, t minus 15 is equal to, okay, then if it's a subtraction, the rules for subtraction, we want to know how many decimal places we have. And so this is 1.543. Looking at this, we have 3 decimal places. So we have something called the uncertain digit. Here the uncertain digit is the 4th decimal place. Here the uncertain digit is the 3rd decimal place. Since we have uncertainty in the 3rd decimal place, we're always going to have uncertainty in the 3rd decimal place. And so we aren't allowed 2 uncertain digits. You remember that from sig fig rules? Sig fig rules, only 1 uncertain digit allowed. And so we're going to get 4 minus 0 is 4, so we're going to drop that 4 eventually. We're going to get 9 minus 3 is 6, 7 minus 3 is 4, 0, 0. So we get 0.0364. How many sig figs do we have here? 2 sig figs. And so we started with 5 sig figs here. We have 4 sig figs here, but our answer had 2 sig figs allowed. And that's because it's subtraction, different set of rules. Subtraction and addition, we don't care how many sig figs we have. We care how many decimal places. All right, so we have that, and now we're going to divide both sides by 1.836 times 10 to the minus 3. So we're going to get t minus 15 is equal to 0.036. Now what should I do with that 4? We're not allowed that 4, right? But what should I do with the 4? Should I keep it or should I just get rid of it? Keep it? How many people say just go ahead and drop it? I mean, anybody? Nobody? You say drop it? Don't keep it? Well, what if you are earning 1.4% interest at your bank, and your bank says, you know, 1.4% is close enough to 1%. And so if they started giving you 1% interest every day instead of 1.4% every day, would you be happy with that? No, because you know what? At the end of the year, you're going to have a significant error in the interest that you were supposed to get. Well, the same thing here. We are going to keep this because each time we drop a digit, that leads to what we call a round-off error. And we don't want to do this. You know, we want to round it only once at the very end, because if we start rounding every single step, then it's the same type of thing can happen. This is my opinion, and so this is why, you know, if you're going to learn something, you should learn it, the way your instructor likes. You could have a different opinion. An alternate opinion to this is it doesn't matter. Some people say, I don't care about this because you drop this, but if this were a 5, we would have rounded it up. And so in the end, it averages out. Some you round up, some you round down, and then at the end, we get the correct answer, or close to the correct answer. But that doesn't always happen. You know, statistically speaking, it might be the case where you're always rounding down. If you're always rounding numbers down, then your error at the end is going to be way off. So if you're earning 1.4% one day and 1.5% the next day, and they round it down to 1 and round it up to 2, then you're okay, right? But what do you think? You know, what if you were earning 1.4 and it never changed, and you kept rounding it? Then you're going to have a significant round-off error. And so what I would like you to do is only round one time at the very end of the calculation. And so we need to carry extra digits. We'll talk about how many extra digits to carry in a minute. But here, you know, the calculator is just 0.0364, right? There's only one extra digit to carry. All right, now we're here. So 0.0364 divided by 1.836 times 10 to the minus 4 equals what? Minus 3? Okay, thanks. 1.836 times 10 to the minus 3. What does this equal? $19.825? 7.
You want me to give the rest?
Yeah, give me the rest.
0.806.
That's all your calculator will give you? Well, that's a pretty decent number of digits. So I want to prevent round-off error, right? So how many digits should I should carry all these? Because if I start dropping some of these, won't that lead to round-off error, right? Well, yes and no. If I carry this many digits, it's okay if you leave it in your calculator. But let's say, oh, I cleared my calculator. If you cleared your calculator, are you going to re-punch in all these numbers? Would you have written down all these numbers? You probably not, because, you know, once you carrying one extra digit is beneficial. Carrying 2 extra digits, better? Yes. Carrying 3 extra digits, better? Yes, but only slightly. And so the payoff starts to diminish with the more digits we carry. So we're allowed 2. If we carry the 8, that's good. If we carry the 8 too, that's better, but not as good as carrying the first one. If we carry the first 3, it's better, but not much better. In fact, if we carried the first 2 versus the first 3, we get the same answer. And so once we get beyond the 3rd digit here, there's no use in carrying these extra digits because it's not going to make any difference in your final answer as it was. And so we'd end up dropping them. And so let's go ahead and just carry 2 digits beyond. Let's say you accidentally cleared your calculator. We're just going to carry 2 digits beyond. So we're going to drop the 57086. If we drop that, if we drop the 5, should I round the 2 up to 3? If I drop the 5 here, should I round it?
Yeah.
According to the rules, yes. But according to the other rule, and the other rule is how many rounding steps are we allowed per calculation? 1 at the very end. So according to that rule, no. And so when we drop this and I repunch it, I'm just going to repunch it 19.82 because that could lead to compounding of rounding errors as well. And so we'll just leave it as is. Not round. All right, so that's the way I do it. Now, you know, like I said, there's differing opinions about this. Petrucci, if you look at the solutions manual, they have 5 or 6 different people doing the calculations. And those 5 or 6 different people, they didn't come up with a consistent set of rules for rounding. And so some of the people who wrote the solutions manual rounded every answer, every intermediate. We call these intermediate answers. So they'd round this, they'd round that. They did so many rounding steps per calculation that the final answer is could be quite a bit different than what you got, you know, had you not rounded. And so you have to be careful with that. Petrucci himself says only 1 rounding step per calculation, but some of the people who wrote, again, the solutions manual did it differently. All right. here, in this case, it doesn't really matter because the next step here is we're going to add 15 to both sides. And so t is equal to 19.82 plus 15. So if we carried the third digit, the fourth digit, the fifth digit, would that have made much difference in this particular case? No. The final answer is only allowed 0 decimal places. So this is going to be 34.82. These two digits aren't significant. Rounding this to the correct number of sig figs, we get 35. I want to see this rounding step. A lot of people, they don't want to show me the number because they just read it off the calculator, round it in their head, and write it down. But I need to see this, because I need to see what the number was before you rounded it and make sure you're rounding correctly. And so what are we after? It's 35 what? Is it degrees Celsius or degrees Fahrenheit or Kelvin? Degrees Celsius? How do we know? How do you know it's degrees Celsius? Because I'd hate for this to be degrees Fahrenheit and come up with a very, very wrong answer. How do you know it's degrees Fahrenheit or degrees Celsius? What it is? Usually we're dealing with Celsius, right? But usually you're dealing with Celsius because you guys grew up on the metric system. There are a lot of engineers out there who grew up on with Fahrenheit, not Celsius. And so they're accustomed to Fahrenheit. And so it just depends on who did this. And so this is the problem with certain of these engineering equations. It's like, you know, for that satellite that went way off course, that, you know, what were they dealing with? Some engineers were dealing with, you know, newtons as force. Other engineers were dealing with pounds, but they didn't write any units, so they just got numerical values. And this equation's not good because what did I say about this equation? I didn't like it because there are no units. And so the only way we'd have to be told what it is. And so we'd have to go back and we'd have to look at the original problem. The original problem says that this is valid in the temperature range 15 to 65 degrees C, and therefore it's got to be Celsius. So you're right. This is 35 degrees C. But the point is here, we shouldn't have to guess or we shouldn't have to read. It should be clearly in the equation itself shown by the units. We call this dimensional analysis, where the units cancel out to give us the units that we want. And so we should have been able to do some canceling here. Instead, we wrote no units and we just did this. I don't know how many points I've deducted that, you know, off exams that, in my opinion, could have been easily fixed had the person written down units. You know, they would have gotten some bizarre unit like milliliters cubed. Have you ever heard of a cubic milliliter? But that's what they would have ended up with had they written down the units, and then automatically they would have said, oh, that's wrong. That can't be. There's no such thing as a cubic milliliter, is there? No. All right. Well, what kind of equation is this? Where did that equation come from? That equation is an example of a empirical equation. Empirical equations, where do those originate from? Do those originate from laws, or do those originate from hypotheses, or do those originate from theory? Where does an empirical equation come from? Observations, good. And so we take observations. When we're thinking about observations, let me talk about observation here. One of the things about this is, you know, we don't know how many observations this equation is based on. Is it based on a limited number of observations or a lot of observations? And so apparently somebody measured the temperature and the density. And we look, when we have observations like this, temperature and density, what do we like to do? We like to look for patterns and or trends. And so for trends, the nice thing is to maybe just graph it. And so we graph density versus the temperature. And we look, you know, there's some interesting behavior between 0 and 15 degrees C. Let's say it was 7. If it was 7 degrees C, 7 minus 15 is negative. A negative times a negative is positive. And so that means as the temperature increases from 0 to 15, the density increases. But once the temperature goes above 15, then this becomes positive, this is negative, so that's going to decrease the density. So the density is going to top out at about 15 and then drop down. Do you see that? And so this would be the mathematical equation that defines this, but we don't know how much data defines this. And so sometimes we don't know how much confidence we can have in this particular equation because there's some information that's missing. And this information that's missing is, you know, a lot of it's missing because otherwise things can get too confusing or too intense for this particular class. But we should talk about it now because certain topics are covered in Chapter 1. And one of those is uncertainty and error. So let's look at error first. You know, there are two types of error that are covered in Chapter 1. Or I don't know, maybe it's uncertainty. Error is probably covered in the lab. But anyway, we better talk about it now. Error can be systematic. Give me an example of a systematic error. This is an example of systematic error. Yes?
You know, faulty scale?
Yeah, a faulty scale. A faulty scale that's always reading off a little bit. And so, for example, if you know the tare button? You guys are familiar with tare button? What does the tare button do? It zeroes the balance. So let's say the balance pan wasn't resting properly and some of the mass of the pan was resting on the bevel or something. The balance could be consistently reading off. But there's an easy fix for that. Do you know what the fix for that is? A faulty scale, there's an easy way to check if your balance or scale is faulty. And in fact, I think in LA they have the LA Bureau of Standards. And for the US they had NIST, which stood for the National Institute of Standards and Technology. Have you heard of it? They renamed it. They went from NIST to some other name, and I can't remember the acronym right now. But at the NIST, what they have is they had a 1 kilogram block of metal stored in a vault. Do you know why they stored the 1 kilogram block of metal in a vault? Who cares about this chunk of metal, right? But they did a lot. And the reason they did is because that's the US standard mass, 1 kilogram standard mass. In other words, that block is as close to 1 kilogram as you're going to get. We buy it too. We buy standard masses, but ours are very inexpensive, you know, like $100 or something. And so we have 1 gram standard mass, 10 gram standard mass, 100 gram standard mass. And before the semester starts, you know, our technicians here, they go into the balance room and then just check each balance. They put the 10 gram standard mass on there. Is it reading 10 grams or not? If it's not reading 10 grams, it's miscalibrated and it's in need of calibration. And so we have standards, standard masses, and other standards to help us with that. And so systematic errors are these errors usually due to miscalibration, one, or poor technique, two. You know, somebody's always reading it wrong. You know, they're looking at the scale at the wrong angle. They get parallax. You know parallax error? For example, when you read the meniscus of a grad cylinder, your eye should be perpendicular to the scale. If you're reading down on it, you're going to be reading too high. If you're reading down low on it, you're going to be reading too low. So if somebody's always reading too low, they're going to be systematically too low. Systematically too high. You got to be perpendicular. That's systematic error. That's due to poor technique. Another poor technique one is some people like to dry these with heat. If you dry grad cylinder with heat, what happens is the glass softens and the volume changes. If the volume changes and then it rehardens, then it's always going to be reading off, right? And so that's another example of a systematic error. Anyway, systematic errors with good technique and calibration can be eliminated. Sometimes systematic errors are very tricky to catch. And there have been examples of that, which we'll probably talk about later. And so they weren't caught for years. And then finally, once it was realized, actually, I'll just talk about it briefly. MIT Lincoln Labs, systematic error, 20 years worth of data. Basically, they had to go back through and reanalyze all that work. Another type of error is random error. Random error, these cannot be eliminated by good technique or calibration, because these are what we call the natural fluctuations in measurements. There is a way to eliminate random errors in theory. Do you know how you can eliminate random error in theory? The way one can eliminate random error in theory is by taking an infinite number of measurements. If you take an infinite number of measurements, then what you'll see is some measurements are a little high, some measurements are a little low, but eventually they might be really high or really low. Eventually what you're going to see are a cluster of measurements that are going to have average out to what we call the true value. And so if we took an infinite number of measurements, then the average of an infinite number of measurements will be the actual value. In other words, it would be an accurate representation of the true value. Does that make sense? But who takes an infinite number of measurements? You know how many measurements people typically take? How many? 2? Well, based on statistics, it's a cost versus benefit. Each additional measurement takes time, right? And so it's like carrying extra digits. When we carry extra digits, that's going to cost you time. But, you know, the more digits we carry, the better accuracy we should get. And before I get too far, what was accuracy again? Somebody had it last time.
How close the value is to the accepted value?
Or the true value. How close it is to the true value. And so the true value is all the digits in your calculator. You know, when you round that, you're going to lose some accuracy, right? And so it's a trade-off between accuracy and time. And so normally, based on statistics, 2 is better than 1 for sure. But 3 is better than 2. 4 is better than 3, but not by much. And so the biggest payoff comes from going from 2 to 3 measurements. And so a lot of experiments you'll see never less than 3. And they typically average 3 because of statistics. All right, so we don't take an infinite number of measurements. We take a limited number of measurements. And so let's take a look at some of these concepts here. We're going to use the dartboard analogy from Chem 4 here. And so we'll consider each throw of the dart a measurement. So let's say one dart hits here, another dart hits here, and the third dart hits right in the bullseye. And so what we're trying to get is we're trying to measure the bullseye, the position of the bullseye. And so this one hit right on, right? But we expect natural fluctuations. We don't hit a bullseye each time. And so there's these natural fluctuations. But what can we say about the accuracy of this? Well, this dart was highly accurate, correct? But what about this dart? Was that accurate? No? Or was this dart very accurate? No. And so one of the 3 darts was accurate. In accuracy, we look at it per measurement. Okay, accurate measurement, not a very accurate measurement, not a very accurate measurement. To help minimize these random fluctuations, what we do is we just take the average, right? Now, if I threw an infinite number of darts, and I'm aiming for this, then, you know, the average should be the true value, the bullseye, which should be pretty accurate. But I'm not throwing an infinite. I just have 3, and then I look at the average, and I go, wow, I got lucky because the average looks pretty accurate. And so the average is, what would you say, here? And what would you say about the accuracy of the average? Would you say the average is pretty accurate? Yes? Yeah, the average is really accurate in that case. All right, this is dart thrower A. And so another person comes. We'll call dart thrower B. And dart thrower B is aiming for the bullseye as well in each measurement. And so let's say the first dart lands here. Is that very accurate? Let's say the next dart is up here. Not very accurate. Third dart is here. Not very accurate either. But where's the average lie? Well, if we look at the average, it would be in the center of this kind of triangle. It would be, let's say, here. How's that average? Is the average accurate? No? Why would you say the average is not accurate? If somebody only showed you the average and they didn't show you each throw, they just said all my throws averaged here. All my throws averaged here. Could you tell the difference? If they only told you the average, then what would you say about the average? If you didn't see this other stuff, you'd say the average is pretty darn accurate. That was right in the bullseye. And so we have this, but you know, when you look at these two, which one has better skill, would you say? A versus B, but when you look at the average, there's no difference. So they're both in the bullseye, and so there's got to be a way, because in science, oftentimes we just show the average, and that's it. We don't show all the numbers that contributed to that average. And oftentimes we don't say how many experiments did you do. You know, is that an average of 100 throws or an average of 5 throws? Right? And so we need something. This is not adequate. We can't just go on the average and say, well, these two students are equivalent because they got the same average. when in fact this person's just lucky because person B, if they did a fourth throw, what would that average be? You know, they got lucky. If they did 2 throws, where would that average be? You see, so just by luck, we stopped at 3 because the fourth is going to throw way off, right? Whereas if this person did a fourth throw, well, it's probably still going to be around in the same general area. And so there's got to be a way to show this because the uncertainty in this average is much greater than the uncertainty in this average. Right? And so is there a way to represent that uncertainty? And there is a way of representing that uncertainty. Because in science, what we do is we try to show these numbers. And so if this is the bullseye, that's the average, what we always do is we do a plus or minus something called the 95% confidence limit. And over here, we would show the average, which would be close to the same average, but this would show much different 95% confidence limit. And so we do plus or minus 95% CL, which we call it. And so this gives an indication of the precision here. The precision, what was precision about again? How close they are. And so this person A is much more precise than person B. And so one way of showing that is by the number of sig figs. You know, we talked about the sig fig showing a high precision measurement versus low precision measurement. It depends on the instrument, right? How many sig figs you can get. Did I talk about that? You know, like 1 gram versus 1.00 grams. You know, 1 gram balance versus 1.00 gram balance. 1.00 gram balance is much higher precision. We have a 1.0000 gram balance over here. In other words, we have 1/10 of a milligram or 1/10,000th of a gram precision. Well, here, you know, how can we show it? Both are kind of in the bullseye. Well, we're going to show it by the 95% confidence limit. This one's going to have a very narrow or tight or small. This one's going to be a very wide or sloppy or big, a 95% confidence limit. In other words, it's the uncertainty in that average. The plus or minus the uncertainty here. Plus or minus the uncertainty here. And so one of the things that's missing, you know, like in that equation, the empirical equation there, we don't have much information. We don't know, you know, were those numbers coming from a person like this, you know, sloppy, and those were just the averages they got? Or was it coming from a person like this where the measurements were much tighter? That you're using higher precision instruments, or what? And so that type of information we don't know. Looking at this, equations. So typically in science, you're going to see plus or minus values here to give you some kind of indication. And whenever we have an equation like this, we don't know how it fits this data. How it fits this data is, and you'll notice this, in science, when you have an empirical equation like this, it's often given with an R squared, which is another statistical quantity. And the statistical quantity just says, well, if I have individual data points like this, and I'm fitting it to some mathematical line, the mathematical line looks like this. The R squared value tells me how well the mathematical line here matches the individual data points. If I get an R squared value of 1, that means the mathematical line exactly matches the data. R squared values less than 1 means some of the data points don't lie on the line. And so we're missing an R squared value here in an empirical equation, in this in particular empirical equation as well. And so these are the types of things. I know initially it's probably a lot, but these are the types of things we've got to think about as we're going along, collecting data, working it up, and doing these experiments. We're going to do some of this. Actually, we're going to do the 95% confidence limit, the formal report. one of the things, you know, this class is supposed to be equivalent to, let's say, UC general chem class, but there are differences. One of the differences is at UCLA they make all Chem 1A level experiments go through full error analysis like this. You know, figuring out what the max errors are. All the numbers have to have a plus or minus. This kind of stuff. Done statistical. We're just going to do it in 1 or 2 experiments this semester. All right, so I said we're going to have pop quizzes this semester. So we're going to have our first one. It's going to be practice pop quiz. It's not going to be worth any points. But the pop quizzes, the way they're going to work is it's going to be open book, open notes, open everything, including you can discuss it with your neighbor or your friends as well. And you can turn it in as a group or you can do it individually. It's up to you. The exams aren't going to be like this, but the quizzes will be like this. And so the first one is, you're going to derive an empirical equation for this data. I'm going to put the temperature in degrees C and the temperature in degrees Fahrenheit. And I'm going to put some data here. 0 degrees C, 32 degrees Fahrenheit, 100 degrees C, 212 degrees Fahrenheit. All right, so we have some observations here. What's the next step in the scientific method? Look for pattern or trend. And then a law. A law is often a mathematical equation that fits the observation. And so give me the law or the empirical equation that fits this based on the scientific method. Okay. I'll give you some minutes to do this and then we'll take a break.